mean by normal forms? We have seen in some grammars where the right hand side is epsilon, it makes grammar harder to use. In this session, let us see what happens if we carry the idea of getting rid of epsilon production to few steps further. To make our task easier, we go for defining normal forms. So, normal forms are nothing but when a grammar rules in the grammar G satisfy certain restrictions, then the grammar is said to be in the normal form. So, where these normal forms are applicable? The normal forms for queries and data can simplify data pre-processing. Normal forms for logical formulas can simplify automated reasoning in AI systems and in program verification systems. It might be easier to build a parser if we would make some assumptions about the form of the grammar rules that the parser will use. So, let us discuss about the different forms of normal forms of the grammar. There are many, but here we will discuss two of them. One is Chomsky normal form and the other one is Gribach normal form. So, what is Chomsky normal form? In Chomsky normal form, also called as CNF, we have restriction on the length of the RHS and the nature of the symbols on the RHS of the grammar rules. The definition of CNF is, given a context free grammar G is equals to V summation RS, this CFG is said to be in CNF if and only if every rule in R is one of the following forms. Either X tends to A, that is only one terminal symbol at the RHS, or two non-terminal symbols at the RHS. So, maximum possible rules at the RHS are either one terminal or two non-terminals. For example, S tends to AB. So, this rule is in CNF form because at the RHS it has two non-terminals. A tends to A, at the RHS one terminal, B tends to B, at the RHS one terminal. So, all these rules are in Chomsky normal form. Every parse tree that is generated by the grammar in the CNF has a branching factor of exactly 2 because it has two non-terminals at the RHS, except at the branches that lead to a terminal nodes where the branching factor is 1. So, second rule, A tends to small a, terminal symbol, branching factor is 1. Using this property, parsers can exploit efficient data structures for storing and manipulating binary trees. Define straightforward decision procedures to determine whether the given string W can be generated by the Chomsky normal form grammar G. And it is easier to define other algorithms that manipulate grammars. So, this is the definition and its application of Chomsky normal form. Quickly, let us see the definition of Gribach normal form. A GNF is in CFG, G is equals to V summation RS, where all the rules are of the form X tends to A beta, where A is a terminal symbol and beta is a non-terminal symbol, and beta belongs to V union summation whole star. If it is star, then X tends to A, beta tends to epsilon. So, it means all possible rules in the Gribach normal form are either RHS consisting of one terminal symbol or a terminal followed by a number of non-terminals. So, here one terminal symbol followed by one non-terminal is accepted, one terminal followed by two non-terminals accepted, and so on. One terminal symbol compulsory, after that you may have any number of non-terminal symbols followed by it, or one terminal at the RHS. So, this is the format or the rules written in Gribach normal form. In every derivation, precisely one terminal is generated for each rule application. This property is useful to define a straightforward decision procedure to determine whether the string W has to be generated by the Gribash normal form grammar G. And this Gribash normal form grammars can be easily converted to PDA with no epsilon transitions. So, these are the two definitions of Chomsky normal form and Gribash normal form, but we will be studying one of these normal forms in detail, that is converting the given context free grammar into Chomsky normal form, CFG into CNF. So, before converting, we can apply some transformations to this grammar such that the language generated by the grammar is unchanged. One simplest transformation is rule substitution. For example, you have x tends to a, y, c, y tends to b, y tends to z, z. So, its equivalent grammar constructed after rule substitution is x tends to y tends to b, y tends to z, z. First time if I substitute y tends to b, then x will be a, b, c. So, next time if I go for substituting y tends to z, z, at that time x tends to a, z, z, c. So, by simple rule substitution, we can go for transforming the grammar from one form to another, but see to it that both are equivalent. Then going to the algorithm of converting the CFG to CNF, there exists 4-step algorithm to convert a CFG into a new grammar GC such that L of G is equals to L of GC minus epsilon. And to perform this, the algorithm used is convert from context free grammar to Chomsky normal form for the given grammar CFG. So, to perform this, as mentioned, 4 steps are: first one, given the grammar G, we have to remove all the epsilon productions like S tends to epsilon. So, this example we have studied in the previous session, wherein all the epsilon productions will be eliminated and the grammar obtained is G dash. Then this grammar G dash acts as input for the next algorithm, wherein we go for removing unit productions. What are the unit productions? Both LHS and RHS having one non-terminal. All such kind of productions are called as unit productions. They must be eliminated because they just increase the number of steps in the expansion of deriving a string. If such unit productions to be eliminated by remove unit productions, then the grammar obtained acts as input to the next algorithm, that is remove mixed. So, what do you mean by remove mixed? As you know, for Chomsky normal form, RHS must be both non-terminals. If it is not, at that time it is called as mixed. For example, A tends to AB. So, it has combination of both terminal and non-terminals. If such type are there, then they must be eliminated and they must consist of all non-terminal symbols. Then the grammar obtained must pass to the 4th algorithm, that is called as remove long. Why remove long RHS? As you know, in Chomsky normal form, just now we discussed the definition, maximum you can have 2 non-terminals. If it is more than 2 non-terminals, then it must be reduced to 2 non-terminals. For example, here S tends to A, B, C, D, you have 4 non-terminals. So, these 4 non-terminals rule must be rewritten such a way that it will be having only 2 non-terminals. And whatever grammar we obtain from G4 is the grammar GC, which is converted from CFG to CNF. So, these are the algorithms, 4-step algorithm used. So, let us see one by one. The first step is removing epsilon productions using remove EPS. What do you mean by epsilon productions? Find a set of nullable variables in G. And what is nullable variable? X is nullable if it has either x tends to epsilon production rules or x tends to A tends to epsilon. It means in turn x tends to epsilon. If such type of rules are there, then they must be eliminated. Let us see one simple example. So, this is the grammar given to you, it is in CFG. Now this must be converted into CNF. So first step from this grammar is I have taken only the rule set. If any epsilon productions to be eliminated. Do you have any epsilon production in this grammar? Yes, that is C tends to epsilon. So what to do? So first find out all the nullable variables. So which all are nullable variables? So first by default C tends to epsilon is nullable. Then if you see, you have B tends to C and C tends to epsilon. It means what? B is nullable. Next, A tends to B, B tends to C, C tends to epsilon. So it means A is nullable, whereas S is not. So the nullable variables are A, B and C. So once we have identified the nullable variables, next what to do? We have to replace the or modify the rules. So first one is S tends to AACA as it is, and in this one nullable rules are A, B and C. So first time if A is nullable, then I will get ACA. If C is nullable, I will get AAC. If both are nullable, I will get AA. Then A tends to B, A tends to A as it is, B tends to C, B tends to C as it is, C tends to CC, C tends to CC and C tends to epsilon. If I substitute epsilon here, I will get C. So these are the rules written. So here this is the grammar obtained after eliminating epsilon productions. Next, so we must go for removing unit productions. So as we discussed, unit production is a rule whose RHS consists of a single non-terminal symbol, that is A tends to B. So if at all there are any unit productions, they must be eliminated. Consider the G dash, which is the grammar obtained after eliminating epsilon productions. Are there any unit productions in this grammar? Yes. A tends to B, B tends to C are the two unit productions present in this grammar. So these unit productions must be substituted. How? If you see here A tends to B, what is B? B tends to C. So we will add A tends to C or C in the A rule set. Next, B tends to C. So B tends to C, C is CC or C. This C terminal is already present in C. So only rule added is B tends to C. But if you see here again A tends to C is a unit production. So substituting C, we add one more rule to A, that is A tends to C. So final rules obtained after eliminating unit productions are yes as it is, no change. A tends to B is replaced as B is replaced as CC, A and C. Then B is replaced as CC, C as it is, C tends to CC. So this is the grammar obtained after eliminating epsilon productions and unit productions. Next is this grammar mixed? If so, it must be eliminated. What do you mean by mixed productions? Mixed is a rule whose RHS consists of combination of terminals or terminals with non-terminal symbols. If so, then what to do? Create a new non-terminal TA for each of the terminal, and for each of this terminal add a rule TA tends to A. So let's see how it works. So this is the grammar as an input for removing the mixed productions. If you see here, one terminal, two non-terminals, a terminal, non-terminal, terminal. So all these rules in red are mixed productions. So what to do? We have to create a new non-terminal for each terminal symbol and add the rule. So which all terminal symbols are there? A and C. So what to do? We go for adding two non-terminals TA and TC, add the two rules TA tends to A and TC tends to C, and then replace all the terminal symbols into these TA and TC non-terminal symbols. Hence, this grammar looks like this. So, once we have substituted all the terminals into non-terminals, the fourth step is to remove long productions. What do you mean by long productions? Long is a rule whose RHS consists of more than two non-terminal symbols. For example, if I have a rule A tends to B, C, D, E, then this rule can be replaced as B as it is, and for C, D, E we take one more new non-terminal M2. What is M2? M2 consists of C, D, E, again it has three non-terminals. So, what we do? C as it is, and D, E we go for writing one more non-terminal, that is M3, and then what is M3? M3 is DE. Now, if we read A tends to B M2, M2 is C M3, M3 is DE. So, this long rule consisting of four non-terminals is replaced by three rules consisting of two non-terminals each, which is already in CNF form. So, given this grammar, if you see here, in this grammar, TA, it is already in CNF form, TC, AC, TC, C, TC, C, A, C. All these in black production rules are already in CNF. The only rules which are not in CNF are TA, AC, TA, TAA, TA, TAC, TA. So, this can be replaced as applying the remove long algorithm. S tends to TA S1. What is S1? A S2. What is S2? S2 is C TA. So, these three rules written for this long rule. Then coming to S tends to TA, a new variable S3, where S3 is A TA. Then S tends to TA, CTA, CTA already has occurred here, CTA, that is S2. So, we have TA S2. So, in place of these three long rules, we have replaced these 6 rules, and finally, the grammar obtained is two non-terminals or a terminal symbol. So, this is the final grammar obtained from the CFG. So, this was the input CFG obtained, given, and after applying all the 4 rules in the algorithm, we have obtained this grammar, which is free from epsilon productions, unit productions, mixed productions, long productions, and it is in Chomsky normal form consisting of 2 non-terminals or a single terminal at the RHS. So, this is one example we have seen converting CFG into CNF. You can see some more examples here. A simple example: apply normalization algorithm to convert the grammar into CNF. S tends to. So, here first step is eliminating epsilon productions. Do you have any epsilon production? C tends to epsilon. On applying remove EPS, S tends to S production rules as it is, B tends to BBC, and if I apply C tends to epsilon, I will end up with BB, which is already there in this rule, and C tends to CC, and if C tends to epsilon, I will get a C terminal symbol. And given this grammar, after eliminating epsilon, unit productions, again here we have only one unit production, S tends to B. On substituting B, we get S tends to AA, B as BBC and BB, then B and C as it is. So, this is the grammar obtained after eliminating unit productions. Do we have mixed productions in this? Yes, we have mixed productions. So, all these except C tends to C are mixed productions. So, what to do? Terminal symbols are A, B and C. So, substitute these terminal symbols by a non-terminal, new non-terminal. TA tends to A, TB tends to B, TC tends to C, and substitute wherever you have TA, A as TA, B as TB and C as TC. And this is the grammar obtained after eliminating mixed productions. Next, are the RHS productions or the rules of length greater than 2? Yes. So here we have 3, 3, 3. So we must eliminate these productions. So after eliminating these productions, the grammar obtained is, you can say S tends to TA, S, TA. So what to do here? S tends to TA, a new non-terminal S1, where S1 tends to S, TA. Similarly, S tends to TB, TBC. So TB and one more new non-terminal S2, where S2 tends to TBC. And one more B tends to TB, one non-terminal. So TB and another non-terminal is S2. So this is the grammar obtained after eliminating all the 4 different types of unused productions, and this is the final grammar obtained, which is in CNF. So we will see one more example quickly. S tends to ABC, A tends to AC or D, B tends to BB or A or Epsilon, and C tends to AC or CC or Epsilon, D tends to AA. Now if you see here, first what we must do? We must eliminate all epsilon productions. So which all are epsilon productions here? B tends to epsilon, then C tends to epsilon are the, so your N consists of B and C. Any other? B tends to A, C tends to, B tends to epsilon, C tends to epsilon, but A tends to D. Is D epsilon? No. B tends to A. Is A epsilon? No. So only set obtained is BC. On substituting these productions, we will get S tends to, A tends to, B tends to, C tends to, D tends to. Yes, A, B, C. Or, so here if B is epsilon means I will get AC. If C is epsilon, then I will get AB. Next time if both B and C are epsilon, then I will get A. Next, A tends to AC or D. If C is epsilon, I will get A. Similarly, B tends to BB or A, or if B tends to epsilon, I will get B. Then C tends to AC or CC, or A is not epsilon, whereas C tends to epsilon. C tends to epsilon means I will left over C, and D tends to AA as it is. So this is the grammar obtained after eliminating epsilon productions. So next is find the unit productions. Which all are unit productions here? S tends to A, then A tends to D, unit production, then any other productions? B tends to A, S tends to A tends to D, B tends to A are the 3 unit productions identified in this grammar. On substituting these unit productions, I will get S tends to A, B, C or AC or AB, or A tends to, B tends to, C tends to, D tends to. I do not have any unit productions in C and D, so the rules will be as it is, AC or CC or C, D tends to AA. Coming to A have AC or D tends to AA or A. Coming to B tends to BB or A is what? AC or AA or A, and this B as it is. S tends to ABC, AC, AB and A. A is substitute all the RHS rules, AC, AA and A. So this is the grammar obtained after eliminating unit productions. Next, what to do? Are they mixed? Yes, they are mixed. How many terminal symbols are there? A, B and C. So what to do? S A, B, C, D you have. We'll add 3 more new non-terminals. TA tends to A, TB tends to B, TC tends to C. And now what to do? S tends to ABC as it is. It's already in CNF form, AB. Then this A is replaced as TA, TAC or TATA or A, because S tends to A is already in CNF form. Next, coming to A tends to TAC or TATA or A. Next, B tends to TBB or TAC or TATA or A or B. Next, C tends to ATC or CTC or C. D tends to TA. Now what we did? We replaced all the terminals into non-terminal symbols if the length is 2 or more. Now if you see, S tends to AC, AB, TAC, TA, TA. So all these productions are already in CNF form. Only production which is not in CNF form is S tends to ABC, which is of length more than 2. So what to do? So this rule I will replace here only. A tends to, what I will do? I will take a new non-terminal. S1 tends to BC. S1 tends to BC. And what is S now? S is A S1. And now you can see all the production rules present in this grammar are in CNF. So given this CFG form, this is the CNF grammar obtained by applying the normalization algorithm.